Today, we are going to continue with the assembly processes. Last week, I gave you my simple assembly of a very simple connecting rod small engine that I found on the web. And I told you at that point that that is not how we teach engineering students. It's a good idea to start, but we are going to continue now to something that is a little bit more to the training that we intend to give an engineer. The connecting rod you did in the drawing of last week looks something like this. Looks like this, but the connecting rod we are going to take into our project and our final drawing will look something like this. So what is the difference between this and this? Well, it is not just beauty or, oh, it looks nicer or it looks sturdier. Engineers are not trained to talk in qualitative terms. We talk in quantitative terms. If we say this is better than this, we do not just say that qualitatively. We are going to say, well, this can withstand a heat of 2000 degrees Celsius, whereas this one can withstand a heat of 1000. That is that's quantitative. We can say this one can withstand a force of 5,000 newtons, but this one can withstand a force of 2,000 newtons. Those are the kinds of things. We can say this one, if you don't remove the material here, it will not be stronger, but if you remove the material, it will be cheaper by so many naira, and it will still be as strong. So the goal of engineering training is that you are not just comparing things in qualitative terms, you are comparing them by specific quantitative analysis. What allows you to be able to do that quantitative analysis is all the differential equations, the finite element analysis, the graphics, and all the things you will take you through in your engineering training. So, whereas something might be very exciting on YouTube and it may look very good, and when it comes to engineering training, the way we look at it may be slightly different. And don't take my word for it. Try and find out why. Because these things are not just a matter of personal opinion. These are things that are life or death, bread and butter issues for training of engineers, which we are trying to do for you. So today, I'll show you how we move from this. I'll show you how to do this one, even though you were already saying that doing this was very easy. You just created a slot and put two holes on it, finish, a small one and a big one, and that's enough for a connecting rod. Here, we just don't have, we have the same kinematic product here, but here you will see that this part is slightly fatter than the rest of the body, and this one is even more so. Not only so, you can disassemble this connecting rod here, and there's a pin here that can be used to hold the two parts together, and that is very important if you are now going to put this thing in an assembly that includes placing it somewhere like here. Let me just show you. If you are going to put it in if you are going to put it inside this crankshaft, you will either have to break the crankshaft or to disassemble the connecting rod. I'm sure you can see that it doesn't look reasonable or sensible to now go and use an axe to start cutting the crankshaft so that you can put the connecting rod inside. So that is the reason why the connecting rod we have must be disassemblable so that I can assemble it back together. This one you can see doesn't have that. So for several reasons, some of which I have said, this is a far more realistic, practical connecting rod than this one. This is good for your drawing, but this is good for your engineering thinking. And this is the kind of thing you are supposed to be aiming for rather than this. So this is helpful for the pedagogical advantage it gives you. I mean, if you are teaching somebody in SS2 to use a free card of fusion, and he can do this, he'll be very happy with himself, of course. But you are engineering students, and you can see you are supposed to be taught to be able to understand why this is what you're looking for, and really not this one. More of the information will come as you advance in your studies. You will not know everything right away. So today, the scope for today is that we are going to look at making the members of our assembly more realistic. And we are going to focus on just the connecting rod. The others are simpler. So I decided to take the ones that appears to be the most difficult. If I can show you how to do the most difficult, it should be easy for you to do the simpler ones. But I expect you in your own, in your project, which will be due in 2 weeks. I've already been told that exams will be starting the second week of March. So in 2 weeks, I expect you to submit your project. I will tell you a little bit more about the project. And I want some of these realisms to show in your project. There will be marks will be awarded for how realistic your projects are, your class assembly projects are. So you can see that a connecting rod can be made from several parts. There can be the connecting rod head, which we call head rod, in the files that I sent to you, or the connecting rod. That is con head, the connecting rod body, the connecting pins, and several other things. In fact, in this assembly, we have 4 parts and 5 components. And that will be important for us to know the difference between parts and components. It is important, and I'm not going to ask you in an exam, distinguish between a part and component. No, you are going to just do an assembly, and you will just discover that you will not be able to do it unless you understand the difference between parts and components. And when you don't understand that you could not do the assembly, then you get a failing grade for it. So it is not going to be a cram issue. It is going to be a practical practice exam that you're going to do. The challenge for the project, kinematics is number 1, realism. You put the kinematic constraints together. The logical assembly requires possibility of repairs. And then you have to have pins to connect components. Even though you can logically connect components without the pins, in practical situations, the pins will have to be there. So it's better to practice that and put the required pins as part of the design and part of the elements that are in your assembly. The continuing mechanics courses you take, for instance, if we ask a question, which of these 2 will break when we use them in our, first of all, this one will not even work because the crankshaft hole is much bigger than this. So you will need, and if you now make this one really, really large, it will become very funny and it may not really work. So you will see why the thing is shaped this way for a reason. And there's a reason why virtually every vehicle you open, the connecting rod looks more like this than like this. They are not all looking the same, but there are serious engineering considerations that led to the choice of what the connecting rod will be. The continuum mechanics courses of elasticity, heat transfer, fraction mechanics, strength of materials, etc., are designed to help you know which to use. Practical and historical experiences have taught manufacturers that lesson. They know from experience, which is incorrect. The training of an engineer is to see why one will work and the other will not, without even spending any money, just by theory and simulation and practical and comparison based on analysis. That is what an engineering training is. We don't have a motor vehicle assembly plant, but what you do is that you just use the theories and the simulations to be able to arrive at the correct thing without necessarily having to make it. One will cost much more than it's worth. You cannot simply make it bigger. You cannot just simply make the whole hair big so that it can be used there. No, there are several things that you must do to decide that this is the way the thing should look like. We are not teaching all that in this course. It will take you your entire engineering degree to be able to know everything you need to know. And sometimes it is also going to depend on the options and electives that you choose. Just like we have said about the connecting rod, we can also look at the piston. You can see that there are two types of piston. This is the piston we have used in our example last time. And this is the piston I am expecting you to be able to design. You will see that the pins, there are pins in both pistons. The pin here is definitely stronger. Not only so, it is more firmly held. The position of the piston holding the pin is much stronger. Now, the question is, can you make this in a single drawing, or does it have to be an assembly? I leave that to you to judge. Try to make it as a simple drawing, and if you don't succeed, try to make it as an assembly, and you compare notes for yourself. I will do this for you, and I expect you to do this transition for yourself. Similarly, in the crank, you can see two implementations. This is the implementation in the one we did before, where I sent you my file. And just in case you do not remember, let us just go and see that. Let's go and see that. You can remember that we have this. You remember that we have this. I already gave you this file where I've done the assembly and the kinematic constraints and everything. And you can decide to take a look at anything you want. For instance, if we decide to look at the assembly, we might decide that we want to just look at the no, let's see which one now. We might in this assembly, we might decide to just take a look at we may remove the static part, remove you can remove the cylinder and the piston. Where's the piston? You can remove the piston and even remove the. Okay, no, let's leave the pin there. We can remove the connecting rod and the pin. Let us just still remove the pin for now. So if you make this bigger, you will see that this is almost like the other big one. The only thing is that we did not put the pin that's supposed to be here there. In the assembly we did, we allowed the connecting rod and these mating holes to be logically linked, even though there's no pin there. That's a dangerous thing to do. It is not very stable. And you will see that if you do it, sometimes you will see that your drawing do not compute. So it is better to put a pin here so that this one will look like a proper crank. So if you really compare this to the other one, you will see it. So let us go back again. Okay. So if you don't put the pin here, you will see that you won't be able to see how these two are really very much alike. Even though the pin here is more realistic and it has some clearances and some other things to make it far more useful than what you are doing on this side. So let's go back to the drawing again. Go back to the drawing. We can decide to remove the crank 1 and crank 2 and the connectors, and we can just show the connecting rod. You can just show the connecting rod, and if we show the connecting rod, let me press 0 here and bring it in. So you can see the connecting rod. This is how it looks. This is what it looks like. This is what the connecting rod that we used last week looks like. You can, because I've given you this drawing, you probably must have done your own drawing by now. So whichever one you like, you'll be able to see this connecting rod. So let me go back again to our slides. So we're back to the slides. So in our slide, you can see this is the implementation of last time. This is the kind of implementation I want you to be able to achieve. The details of how whether you use a triangular shape or a more rounded shape is a matter of choice. You can choose one. But what is important is that you can see that this is a far more robust crank than this one. So what changes can you observe in the more steadily made example? Can this be executed as a single body or as an assembly of components? Try both and take whichever one that you like. For instance, if you draw this triangular shape, round it up here, and do whatever it is a simple padding here, and this is exactly this one and this are the same. This one, you can use a single revolve to do this, or a combination of revolve and padding. And then you can do them separately and use the methods that we are demonstrating now to do a complete assembly of this sub-assembly. You can treat it as a sub-assembly. Now, if you continue there, and instead, after you have finished a single engine, if you make more engines and just expose the crank part of it, you get a crankshaft. Now, if you try to draw this directly, I wish you the best of luck. I don't know how you'll be able to achieve that if you try to do this directly, but it comes so simply and so easily from just doing your assembly, and this one will come out of it. So drawing a crankshaft is a very bad idea, but bringing out a crankshaft after your assembly is a very simple thing to achieve. So you can see that experience really shows how to do some of these things and not just theory. It is your practical experience in doing them that will show you which one will work and which one will not work. So what FreeCAD shows? In FreeCAD, you are limited to a single body. How do you make parts that are not so simple or that are in fact complicated? How do you make them? When parts are not so, and then you are also limited in FreeCAD to simple sketches. I want to go to the chat room, maybe if I may. I want to ask a question in the chat room. So let us just visit the chat room briefly. And let me just ask you a question. I will type the question so that people will not be asking me later what was the question, what was the question. So where's the chat room? Okay. So the question is, how many people have had problems such as wire not closed when trying to make a pad or a revolve or something? Let me see an indication. Have you ever had in your FreeCAD that you try to do a pad and you are faced with the pad, the sketch just disappears and you are told wire not closed? How many people have had that problem? I'm still looking for answers to my question. Are there people in the class that have had problems with when you are trying to do a pad after a sketch and you are told the wire is not closed? Has anybody had that problem? Adeboye, I don't know whether you are answering that you have had me or you are asking that you have had a problem. Please, can you set a sentence to make what you are saying clear? Is this class active? Well, have you people been doing your drawing? The time is almost ending, and not practicing your drawing can actually be problematic. What I am saying here is that many of you have not been practicing this thing, and well, we'll see what kind of projects we submit in the next 2 weeks. So today is Thursday. So 2 Thursdays from now, your project will be due. It will be written to you. What is 2 Thursdays from now? Let's say 2 Thursdays from now, project will be due. Let's see what the time is. what the date is. So when we add 14 to 19, that is 20. That is 14 to 19 will give us 33. So when we remove 28 from that, that will be 5 days into February. February 5, and March 5. Your project must be submitted before March 5. So let me write it for you, because apparently many of you are not practicing. I do not see enough people practicing for this course, and by February, by March 5, we are very close to your final exam, and that at that point you'll be glad if you have been practicing. So you are limited in FreeCAD to simple sketches. The sketches of FreeCAD easily get problematic when you try to create paths, revolves, locks, and sweeps. The strategy is to keep everything simple and look to assembly, shape binders, etc. We will look at the subassembly of a connecting rod in today's lecture. To prepare for your examination, implement this in your project. Up to 5 people may collaborate and present a single assembly project. The responsibility of each member will be clearly stated in your submission. So it is the duty of the class to explain what each party is doing. Even as you collaborate, note the following. You can keep the full drawing of the group project individually and own it, provided you can reenact the drawing on your own. 2, the fact that the whole class, the whole team participated, you have to take it, study it, and make sure you can do it all by yourself. Number 2, you can extend each element or the whole assembly by yourself. 3, you can remove and change any component or feature of a component on your own. If you cannot do the above, do not own the project. You do not own the project. Own projects are required to face the examinations. You are bringing those projects to the exam, and the questions are going to be on the project. And the other drawings, like the impeller and the volute and the other things you've done, we will ask questions that will be specific to what you have done already. And only submitted own projects can be used in the final exam. So if you start changing things from something you have not yet submitted, we will compare what you submit before the exam to what you are using in the exam. If they are not the same, you are going to be penalized heavily. So there is no escape. You must do one and the other. So let us go step by step now. How do we make a part? I have sent to you the files of the component of the parts that from where components are created. So I've given you my own. You can use it to start, but you can only get marks for additions you make on it. Any improvements will be rewarded, but if you just give me back what I gave you or give me something worse than I gave you, I'm sure you know what marks that will attract, 0. So it is good for you to practice. It is good for your training, but what will earn you marks will be to advance from it. I've showed you, for instance, how to advance your connecting rod, which is the cause of this lecture, how to advance your crank, how to advance your piston, and other things that you might use in this particular assembly. So if you want to make a part, these are the steps. Starting from a free card, a completely blank free card page, you can create a new document. When you create a new document, it will give you a document without a name. You can save that document and give it a name of your choice. And then inside that document, if you are already in the part design workbench, you can go and pick the new part and create a new part for your document. After you have created a new part, you can create a new body for your document. From here, you can begin with the sketcher, make features to your tip solid, which is the body of the part. Those are the steps. Follow these steps. If you don't follow these steps, you are going to, there's some pain ahead. Save each part as a document by using the file save method. It is from there you open the part to an assembly, as we shall later show. Do not forget, it is components only that can be assembled. You cannot assemble bodies, you cannot assemble parts, you cannot assemble documents. The only thing FreeCAD will assemble are components and components only. But what are components? Components are bodies in a file that are referenced from the part. So even though you are not assembling bodies, you are not assembling parts, the components you are assembling are related to bodies and they are related to parts. They are inside your document. Alas, FreeCAD is sometimes not consistent with its nomenclature. We shall try here to retain a consistent method while showing step by step what you need to do to achieve the simple assembly of a connecting rod sub-assembly. In the present case, we have a connecting rod which by itself is a sub-assembly. It contains the following parts in my own naming. I named something head main, another one rod head, third one small end, and lastly con pin. That is how I named them. And the head main looks like this. This is the part of the big pin head of the connecting rod that stays inside the big pin of the crankshaft. It is to be connected to the con head with two pentagonal heads. You see, the pin here, we have the head of a pentagon. So you need to do this. The proper holes to accept this are provided as shown. The head is a pentagon, the rest of the body is a cylinder. So you can see it starts as a pentagon head, but the rest of it goes in there as a cylinder. This will mate with the con head on one side and be fused with the small, it will mate with con head below and it will fuse with the small end at this point. So this is the rod head or con head, whichever, I don't know which one. Sometimes I say con head, but you can name your own and be consistent. It is this area and this area that will join the other side and we fuse to a pin that will be that will force the two of them to stay together. You can decide to make them mate without that physical pin, but what we are saying is that the correct thing to do is to put a physical pin there. Unlike our simple assembly done previously, the connecting rod is a well-designed part that must be optimized for weight and transmission of forces in a well-organized manner. The optimized shape is the result of engineering simulations. What's important here is that you do not usually disassemble the crankshaft. Any maintenance in the engine that involves the connecting rod requires that it be removable. The work of breaking it into two, as we have done here, is to facilitate the action. So that is why instead of a single part, there are two. Here we show the mating surface of the connecting rod head, where it is joined to the other part by a pin. The small end is usually the main part of the connecting rod. In FreeCAD, you often get errors of unclosed wires once the drawing becomes a bit complex. The separation we effected here is to demonstrate that by using the assembly feature and parameterizing your drawings, you can avoid these errors by having simple parts that are connected by simple binders so that a change in one part is reflected in the other so that there is no loss in separating them into simpler components. If you do not have difficulties in creating the top part as a single object instead of two, you're welcome to do so. but this separation may be faster for some people. The cone pin. You can see this pentagon head here, and then so these are two paddings. You do a padding up here with the pentagon sketch, and you do a padding down with the circular sketch. That's all. And then at a particular point here, you create another sketch surface on this plane, and you pocket through to get this. This is a very simple thing to do, but do it. Don't just take it simple. We use two connecting pins. I have given you the file, so you can take it and edit the paddings, and you see how long they are and all those ones, all the dimensions you can find in the files that I gave you. It's a teachable moment to see the difference between a part and a component. A design pin itself is a part. Two incarnations of that pin we are bringing to assembly are components. So what we are saying is that when you do this design, what you have designed is a part. But when you bring two of them into the assembly, one here and one here, they are now components. They are components referring to the part. And the reason why they are components will be made obvious shortly. They are not parts, they are components. And a component doesn't have any information. All the information is in the part. If you change the part, it will be automatically reflected in the component, as we shall show you. And you'll see why it is very important to notice the difference. Assembly steps. The first step in the assembly process is to remain in part design workbench and bring in all the components into the design. Actually, it is all the parts you are bringing into the design, parts. But there is a confusion even in the way FreeCAD talks about parts and components. They are often used interchangeably, but it is teachable for you to know that they are not the same thing, because that can be the difference between your drawing working and your drawing not working. What you really bring to the design are the parts, and you will see why sometimes we use the word component instead of part. This should be a complete part with a body that ends in the tape solid. Again, in the nomenclature of FreeCAD, you cannot assemble bodies. What comes into assembly are components that point to parts you have created. A component is a pointer to part. So for a single part, you can create 5 different incarnations of the part, and there are 5 different components that you can bring. For instance, you will see that in this particular example, we are going to bring 2 copies of the pin into the assembly. Those 2 copies are components, but the pin itself is a part. It is possible to get to this point from several methods. For example, the cone head and the cone main. To break the cone head and the cone main into 2 different parts, we started from the same part. And if you go through the model history of any of them, you will see how this one happened. For example, the cone head and cone main and head main were from the same part. There are several ways of breaking this into 2 parts, as we have done here. Last week, we talked of taking them to the part workbench and allow Boolean operations and cutting planes to create Boolean fragments, from where you may then pick the parts you need. We are not going to use that method here. We are going to use a method that is more parametric, and you remain within the part design workbench. This is how it happens. If you go through the the model history of either of these, you will find that at a point, you are going to see a part like this big one here. Now, what this one is a slice of it here and a change of the head here from circular to pentagonal initially. That's all. So this one is this, where it has been sliced in 2. This one is the bottom part of it. And you can get this picture from either of these 2 files, both of which you have. I've already given you both files. So you can see how that slit is done. So in this one, when we did the slit, we removed the bottom part. And this one, when we did the slit, we removed the top part. That's how we got this at this. And it's very efficient and effective. So, and it is not as complicated as the code, as the fragment. That's not even the reason why I'm using this method. The reason I'm using this method here is that you can continue doing your parametric design. For instance, after splitting them, it was after the split that I came to do this end here. You can see that this one is no longer looking exactly like this because this hole here has now been distinguished from the one from this one. So you can see the difference between them. And this can be done later. And how do we do this? You just put a pentagon here. You put a pentagon here. And when you put the pentagon, you pocket it through like, I think 5 millimeters here. And that's it. So that will help you to be able to sink the head of your pin inside the body. And that is something that will make the thing a little bit elegant. We break these two parts into two by retaining the part design tools. One advantage of the part design is that you can continue working on the fragments after breaking them. In the Boolean method, I've not yet seen how you can continue the parametric design further downstream. It says you can't, so I have not been able to do it. So I prefer to stay in the part design rather than go into part to do that. In this case, you may observe that the pentagonal head space in the main body is created after fragmentation. You can find that in the file I gave you. I personally do not like to lose that advantage. That is a preference. In the part design workbench, this break was done by simply creating two files of the object, pocket to remove one side, pocket to remove the other, name appropriately, and it's done. It is easy and straightforward, and I encourage you to try it out. So to get to the assembly, you can open all the files and get a model tree and dialog that looks like the next page. The only other thing we did before reaching this page is that we created and saved new document to receive the assembly, move the assembly workbench, move it to the assembly workbench. In the assembly dropdown, launch the assemble component dropdown. I will show you how the thing looks like, or maybe if I have the time or the disposition, I can just do it in this class. You get a screen that looks like the next one. So in my own case, because I have designed the head main, the rod head, the comp pin, and the small end. So I've done all of this already. So I just open my free card, and when I'm into my free card, I just mark all these 4 and open them all at the same time. When I open them at the same time, they all come in, and it is from then I am going to get my parts and the components. That is one way. There are several methods that you can use. This is just one method that works. The parts file of the components to assemble must be first brought into the scope by loading them all into your present work. You can load them. You can also load them one by one. It's just faster if you can load them all at once. Assume you are starting from a fresh free card session. You can load these files one by one or at the same time. Assume the part design workbench at the start. These files, in my case, are head main, rod head, comp pin, and small end. Next, we create a new document. After you have loaded these ones, you now create a new document and name it Conrod Assembly, simply by saving the file under the name you want. So when you create a new document, you say save, and it prompts you to give it a name, and you'll see it on your model tree immediately. We now move to the assembly workbench. You create a new assembly and activate the assembly to obtain the next page. You activate the assembly. How do you activate an assembly? You double click on it. So you open an assembly, and then you open an assembly. You are going to get, for instance, comp pin, head main, rod head, and small end are the 4 files that you brought in. This is a file that you created and named Conrod Assembly. After that, you move to the assembly workbench. When you get to the assembly workbench, you choose new assembly. When you choose new assembly, and then you now activate the assembly. After activating the assembly, you go to the assembly drop down and you say insert component. insert component, it gives you two opportunities. He said insert component or new part. If you say component, if you go to new part, it expects you to create the part. If you say component, it knows that the part is already created. If you click on that, you are going to get the next page that I'm going to show you now. And maybe after we come back from break, I will show you, I will go through this directly for you. But remember that I've already given you all the files that are in this talk. So when you do that, you'll see that all the things in those 4 files, you see the comp pane, there's a part, the head main, there's a part, the rod head, there's a part, the small end, there's a part. It is from these parts that you are now going to create components. So if you click on one of them, it's going to bring a component of that part into your assembly. If you click on this, it will bring a component of that part into your assembly. If you click on this, it's going to bring a component of that part into your assembly. If you click again, it will give a second part into your assembly. You can make several components from each part. So when you have a part, a component is simply a pointer to a part. And you can have several pointers. So you can have 3 or 4 things that are pointing to the same part, so that when you change that part, all of them will receive that change immediately, because the part doesn't have anything, the component doesn't have anything. Everything is residing in the part. Don't try to bring the file, the document into your assembly. It is the part. Remember, it's not the document, it's not the body, but the part that you bring into your assembly. So when you begin here with a con head, for instance, that is just the first thing you see. Do you want to ground the first inserted part automatically? You need at least one grounded part in your assembly. Yes, always, never, no. The correct answer here is not no. It's not never. It's not always, but yes, you want to bring the first part, because I have decided that this head is going to be my ground. Every other thing will be grounded to this. So I answer yes here. But if you make a mistake there, you can always unground what has been grounded. So it is not a death sentence if you make a mistake. I do not bring in the object file. Instead, I bring the part inside the file. Here is the important point. You do not assemble bodies, but components that are pointers to parts. The bodies are inside the parts. You are prompted on whether you want to ground the first instance as shown here. The correct answer is yes, and not always in this case. In all other cases, the answer will be no. So after you have grounded the first thing that you are bringing in, the answer for in most cases, the answer is that you do not want to ground. You just want to link and connect the kinematics with the other things that are already there. Every assembly, grounding the first component, every assembly must have at least one grounded part. In our case here, the rod head is grounded, is the grounded part. Only one pointer to it is required in this assembly, and it must be grounded. The framing of the question is important. You can bring in more pointers, that is more components than one in the same part. If you do, this question is asking if you always want to ground the first component of a part. If you always want your first component of a part to always be grounded, the answer is no. You don't want them to always be grounded. But for this part, we want to ground, we want this one and only this component to be grounded. So that's why we answer yes. Notice that you can later unground a grounded component if necessary. You can now bring in other components by choosing the part section of each. By choosing the part section of each part, you are adding a component of that part into your assembly. In this picture, we have brought in head rod, one component. From the part head rod, we bring one component. From the part rod head, we bring one component. For the part small head, we bring one component. For the part con pin, we bring two components. So it is here. So it is here that you can see the difference between the component and the part. Because if you are only bringing one of everything, it doesn't seem as if there is a difference. And that is what happens most of the time, because you are only incarnating one component from a part. But when you are doing more than one, then it is clear that a component is different from a part. But internally, what the computer stores in a component is completely different from what it stores in a part. It is as important as the difference between a car and its registration. If somebody is to take your car away and leaves you the registration component, the registration papers, you know that it's not the same thing. The registration is not the same as the car itself or anything you have. The paper say you own it, it's not the same thing as your real physical possession of the thing. The physical thing is the part, and the registration documents is the component. So when you are dealing with components, even though it looks like the part, it is not the part. It is just a reference or a pointer to the part. They look like they are in this array, but you can select any of them and look at the data on it. So when you bring all of them in, they are sometimes they are on top of each other, and they are just like that. So, but if you look at your assembly, you will see that they are named part 001, part 002, part 003, part 004. So there are 5 of them, 1, 2, 3, 4, 5. But there are 4 parts. There are 4 parts, and these are all components. Again, that's why I don't like the way the FreeCAD sometimes label things, because actually what is called part, calling part is component. It should have been better to name this component 00, component 001, component 002, component 003, component 004, and component 005. It will explain what is happening much more accurately. And I will try to do that when you come back from the break, so that you will understand how this thing actually works. So you can have component 001, component 002, component 003, component 004, because the components are just pointing to the parts. And from that, you can do the joining and other things that you may want to do. What else? Let me see what the next one is. You can examine each component, and you can examine each component by clicking on it and looking at the data page. The data page will tell you what part it belongs to, what part it is pointing to. It will give you the placement, the location, and several other information you will want to know about it. You can have more than one component point to the same part. That means it's not a new drawing or design. Every information about its geometry and features are resident, not inside the component, but in the part. If there are 2 components of the same part, what happens if you change? Any changes to the part will be reflected in every component pointing to it. I want to avoid the word referencing, because sometimes the word referencing can mean something else. The component is simply pointing at the part and giving you a copy of what it sees. So if you change the part, all the pointers will see something new. You can have several components and assemble them, even if they are of the same part. Important to know when you are dealing with a part or a component. One thing that blurs this distinction is that you use most parts only once. If you are using parts only once as components, it appears as if components and parts are the same. But be very careful. The system does not take it that way. It distinguishes between components and parts. So we are at 10:52 right now by my time here, by my clock here. So what we are going to do is that we are going to go on a break, and we'll be back from that break at 11:15. So you can take your break now, and at 11:15, you get back. You get back to class. So get back to class at 11:15, and I may do a small demo for you, then we can move on. So I'm going to stop my video now and mute myself, so you will see it again. Let's get to the end of this. and I will see whether I still have time to just do a simple demo for you. So this is how also by now you would have inserted all the components needed, and then you are now supposed to now begin to constrain your design. So for instance, most of the time here, we're just going to use fixed constraint. So if you want to make this one and this one to act together, you're supposed to find the center of the circle that was the sketch for this curved surface, which is the same as the center of the circle that was for this curved surface. If you choose them for both of them, they will just this one will just come and stay on top of this. That is that simple. If you can find that for these two. And you click OK, and then you can begin applying the kinematic constraints for the other things. The following joints are available in FreeCAD release candidate 2 that I'm using. Grounded. When something is grounded, there's absolutely no motion, and that is the reference from all other bodies and motions. When it is fixed, that is the motion between the two parts fixed to each other will be zero, no motion. And in reality, it is an enforcement of welding or bolting. Revolute, a rotational motion between the two. Cylindrical is a combination of rotational and sliding motion. We will take these things are easier saying than just described. I've done a table here for you where, because unlike the kind of joints that are available in FreeCAD is more than that is what I'm used to in Fusion. You have fixed, revolute, slider, cylindrical, ball, planar, parallel, distance. And these are really, and then the uses are on this side. Now, before I go into a small demo before we end today's class, in your project, I will expect you to, just as we have done the piston sub-assembly and the connecting rod sub-assembly I've given you, you could also do a piston sub-assembly like this one. In this particular one has two piston ring spaces. You can have more than that if you want. It can be 2 or 3, sometimes 4. And then you can see that inside the piston, the rigid pin, the rigid part holding the pin for the connecting rod is very strong. You can see that. And if you cannot do that by a single, there are several things you can do here. You can do a solid or revolution, and you can do a revolution and several extrusions before you get there. And they can be different parts that are actually assembled together using fixed assembly joints. So the choice is yours. Let there be a holding in your own sub-assembly. Let there be a holding system to which the small end of the pin is joined, and you can add 2 or more spaces for the piston rings. Similarly, you can also have the crank. It's slightly more elaborate here. And as an example of the extension of the crank to make it more realistic. Here, the big pin is expanded to accommodate a spacing of about 5 millimeters on each side to accommodate the big end of the piston. Do this another enhancement. The edge is more triangular here than rounded. Make your own choice. You can use either one. The stator of the cylinder are both grounded, and in reality, they are part of the static parts of the engine block. So you might you can connect the two in your own elaborate design. The piston, the crankshaft, and the connecting rods are moving parts. Do a manifold to contain the moving parts, and then you are relatively free in the way you design your static parts. So as long as there is enough space for the moving parts to stay. That is the end. So what I will try to do now is to go to the FreeCAD, my FreeCAD and see whether I can just successfully give you a demonstration. Sometimes when I try to do it, the amount of bandwidth on my computer and internet make it a little bit difficult. But let us see whether it will work this time. So I'm assuming that if we want to do the assembled con rod here, we can decide to close. Let me see what we have done here. Okay, you can see that the pin we have put here is slightly, let us try and expose this pin and use that as an example of how things should look. If we expose the pin, what we need to do is to, let's see, what is part 4? Part 4 is the top. That's not what we want to do. We don't need to remove that. Part 3, let's see, part 3. Okay, that's part 3. I want to retain part 3. Let us see part 2. Aha. So you can see part 2. If you look carefully, you will see that we want this hole. We want these 2 holes to move down a little bit and come out. We want these holes to come down out. And let me see whether the assembly is activated, first of all. Let's see if the assembly is activated. Let's see whether this one can move up or down. This is fixed. Let us see what we have there. What have I? Okay, let us see. This part is okay. This part is okay. Let's see the part 2. Okay. So I want to query the joints. Let us look at the joints. See, if I take the joints, if I activate the joints one by one, the parts that are joined together will be solid. The other parts will be okay. The other parts will be transparent. So that's how you know what the parts are. Okay. So let us go back a little bit. Isolate. Cancel. I want to go back to the part, the joints. Let's see this joint. For instance, there is a joint, for instance, there's a joint between this joint, this fixed 005 is a joint between the pin and the top of the connecting rod. That's why every other thing here is, you can see that every other thing here is transparent except this part and this part. Those are the 2 that are joined by this. So what we are going to do, let us remove that joint. Let us delete the joint. If we delete the joint, let's see, has the joint been deleted? Okay, I've deleted that joint. So I want now to go to the assembly. Okay, I want to activate the assembly and then try to see whether I can bring back the joint. Okay. So I want to create a cylindrical joint. I want the cylindrical joint to be between, this, let's see. I want the cylindrical joint to be between here and here. Let's see whether that will accept it. Let's try again. I want the cylindrical joint to be between this point here. Okay, so it has brought this in as a cylindrical joint. Let us say that is okay. So if there's a cylindrical joint, that means that I can move it up. I can move it up or down, and I can also rotate it. I can also rotate it inside this place. So because it's a cylindrical joint, it can move up or down, and it can also be rotated along the. So it is necessary to have that kind of joint so that I can rotate this this pentagon into the correct position. So you can see now how that kind of joint allows me to move this pentagon to the correct position. So if, yes, I've now moved the pentagon to the correct position, but let us see what happens. What then happens below? What happens below? See the hole here. The hole here is not coming out. And we don't want that. There are two things we can do. We can go to the pad that created this part and extend the position of this hole here. So what I'm going to do is that I'm going to go to the part. That part is the, let us see where I see the part. Let's see the part. The part is the comp pin. So in the comp pin, that is the component here. So let us go to where we brought it into the, let's see where we brought it into the drawing. Okay, this comp pin. So let's see whether we can see it on the assembly. That is the body. That is a part here. Let us see that part. Let us see whether we can edit that part. Okay, if we edit this part is dealing with the head. We don't want that. So let us say cancel. Cancel and go back again to the assembly, to the model tree. On the model tree, let us look at part 001. Let us try edit part 001. Okay. That is what we looked at before. Okay. The model tree again. No, of the complaint. So let's see the pocket. Let us edit the pocket. Okay, that is the pocket, but that is not what is important. What is important is the sketch that created this round. Okay. Let us go back to the model tree again and look at that, for that pocket, what is the sketch? Let us edit this sketch. Edit this sketch. Okay, so in the sketch here, you see that we can deal with the hole that created that thing and how far down it is. So let us increase this now to 40. Let us increase it to 43. So let us increase to 42. 42. So it has brought that thing down a little bit to 42. So let us click OK and close it. So let us now go back to the drawing. Let's go back to the assembly and look at the, go back to the assembly. Let the assembly be. So you can see that just that moving it down a little bit has brought this hole out. Let us see what is happening to the other pin. Go to the other pin. You can see that when you go to the other pin, that same thing has moved this back down. To show you, to really demonstrate what is happening here, let us make this pin longer. To make the pin longer, we go again to the assembly. We leave the assembly and we go to the part of the comp pin. We make the comp pin. So let us make this longer. To make it longer, we try to edit the part. And let us see the part 001. Let's see whether that part 001 can be edited. Oh, no, that's still not what we want. Okay. Go back to the model. Let's see which part. Let's see this part. Let us edit this part. Okay, so this part is minus 45 in length. Just to make it funny, let us make it minus 80. or minus 70. So if we make it minus 70, so, and then let us also edit, okay, if we say that is okay, and let us see what happens. Let us see what happens now if we go back to the model. We go back to the model and look at the assembly. What happens in the assembly? Make the assembly so you can see what has happened. We changed the length of the part inside its component, and you can see every component that is referencing it. You can see how long these ones have become now as a result of what we just did to the part. So that is what happens. So whenever you go to edit something on the part, it will show up in whatever you have done to the model. That is an example of how it works. So if you want to take a look at any other part, whatever you do onto the part will be shown in the component. If you make this shorter, it will be shorter. In fact, in the files that you are given, unless it has updated itself, if you downloaded it very early, this length is not long enough. So all you need to do is to go to the part that you brought in, edit the padding you did there to the correct length, and it will be okay. So that is it. So this here you have, like I said, this is if you activate the assembly, you can easily move this. You can easily move this in up or down, and that will be the way you can do it. I will just spend some time in the chat room and see if there are questions about this drawing, and then about your project and about submission date and other things that we may want to talk about. So I'm going to go to the chat room and see whether there are people who have questions for me. Oh, of course, the image can be programmed. Okay, you can use Python. You can use Python to do both. But by the time you are programming in Python, you already know much more than the person who is doing part design. Anything you cannot do in part design is very unlikely you can accurately program it in Python. Unless even if you want to use artificial intelligence, try. If you can use AI to create it exactly, accurately in Python and give enough, by the time you can prompt the AI enough to do this thing, you would have been able to create it directly. Yes, I want you to limit your questions to today's lecture. while I want you to limit your questions to today's lecture, David Oloketuyi, there is no involute pump. The word involute means a completely different thing from volute. Please check your dictionary or AI to tell you the difference between volute and involute. A volute is a geometrical object, it's like a pipe that is very in dimension and is in a spiral shape. That is what we call a volute. An involute is a particular curve used in gearing systems. It's a mathematical definition. It's a mathematical curve. So involute is not the same thing as volute. So David Oloketuyi, please notice that every set of students confuse the word volute with involute. Well, if there are no questions, I'm ready to go. And I'm assuming that you understand that you are supposed to practice what I've given you today. I hope you can all open the files that I've given you. You can bring in the objects and then do the linking and the constraining with joints. And you know the kind of joints that you can use. And there are several joints there. But for today's class, most of the time we use fixed joints, except in the pane, where we use the cylindrical joint. And you can see that if you go to edit the pane from in the file that you brought in, you can see that you can change things there that will reflect immediately in the components to which they belong. So editing a pane and editing is the same thing as you don't edit the components directly, you go and edit their path files. When you edit the path file, everything will show in the component. You could even edit it on the system without even opening it, because each time your assembly will find where the file is located and it would update itself. If it doesn't update itself, you can tell it to recompute and it will update itself. So that's it. So well, it's 11:42 now by my time, 11:41 to 11:42. It is likely that we can now call it a day. And please remember, class, 2 weeks, all the projects are due. The assembly project is due in 2 weeks. The assembly project is going to be given a substantial mark. Not only so, you have to bring your work into the exam, and questions will be asked that will demonstrate whether you actually did it yourself or not. If you didn't do it yourself, or you don't know how to do it, the result will come out in the questions that you'll not be able to answer. Please, you have the opportunity now to do what you need to do, and bring these things in in 2 weeks' time. By the time you are on March 5, it's already too late. March 5, you must submit before March 5. Submit to your class rep, and your class rep will keep a comprehensive list of people who are in different groups that are submitting, and we will check. Once we check and there's a problem with it, we will blame the class rep. So the class rep make sure that, because that lazy students will always hide and say they submitted when they did not submit, and the result is always the same. So make sure you submit your project in full. It can be opened, and your class rep has taken measure of it, and you have a paper, a piece of paper that listed the people in the group and precisely what each person is responsible for in what the class is submitting, in what the group is submitting. If you copy, if 3 groups copy the same project, I will give them their grades and divide by the number of groups that copied it. So no problem. So make sure you do your own work. It is easy for me to know whether you are doing your own work or not. And I can see that many times you people have been lazy with doing this thing because all the questions I've asked, your answers to them shows that you have not been doing your work. But time is almost over and you have to do something now or you will repeat the course again, which is not very, you should be making progress rather than repeating the course. So I'm going to leave now. So after I've left, you can turn off the group.